In the previous video, we talked about polygons. In this video, we're going to the next dimension, 3D geometry. So first, here are some basic formulas you're probably familiar with, like volume surface area of a cube, base diagonal of a cube is root 3 times the side length, rectangular prism formulas, the cylinder formulas, and cone formulas as well. Here's a formula you probably are not familiar with, and that's the volume of a regular tetrahedron is root 2 over 12 times the side length cube. The volume of any tetrahedron is 1/3 base area height, but for a regular one, there's a special formula, root 2 over 12 s cubed. And for a regular pyramid with all sides equal, square base pyramid, it's root 2 over 6 times s cubed. Okay, so let's first take a look at a volume. Let's take a cool volume problem. And this is a very standard technique in these types of volume problems. A regular hexagon of side 6 has an isosceles triangle attached to each side. So what we're going to do is we're going to fold each of these triangles and make a pyramid with the hexagon as the base of the pyramid. When you fold all these triangles up, they're going to meet at one point. You fold them all up, you meet at one point. And this is going to form a pyramid. And I'm trying my best to draw something in 3D. This is a pyramid, and because of the fact that each of those isosceles triangles we folded up at a side length of 8, each of these pink segments is going to have a side length of 8 as well, because we folded them up to form this pyramid. So now the question is, what's the volume of this pyramid? So firstly, because we have a regular hexagon as a base, we know the volume of a pyramid is 1/3 base area times height. What is the base area, first of all? Well, we know from a polygons video that the area of a regular hexagon, well, we can divide into 6 equilateral triangles and stuff. 6 times root 3 over 4, side squared, which is 54 root 3. So we found the base area. Now, all we have to do is find the height. And the key thing about this problem, well, let's first of all draw what the height is. What is the height going to look like? The height's going to look something like this, where this is h. Now let's actually draw a separate figure, and this is the entire pyramid, but this new figure I'm going to draw is just going to be that of the base of this pyramid. So what's true about this base of this pyramid? This purple point, as you can see, is the same. Notice that in our original pyramid, if we draw this line here, that's going to be this part of the base, on the base of the pyramid. These two things form a right angle. And it may not seem like that in the diagram because it's a 2D visualization of a 3D object. But if you can imagine a flat plane and you have a height sticking up, it's going to form a 90-degree angle. So that's 90 degrees. And we know the length of this pink segment is 8. So to find the height, all we have to do is find this segment, and we can use Pythagorean theorem. So how do we find the length of that segment, or this segment which is shown on the base of the polygon? Well, notice that this purple point is the center of the hexagon. And if you remember from the previous video, we can divide a regular hexagon into 6 congruent equilateral triangles. And because this is the center of the hexagon, it's going to form it's going to be the point from which we can form 6 equilateral triangles. So from the center, we have an equilateral triangle here, and that gives us that these two segments are both 6. Aha! This purple length over here is 6, h is shown, and 8. And we can now use the Pythagorean theorem. H squared plus 6 squared equals 8 squared. Therefore, h squared is 64 minus 36, which is 28, making h equal to root 7. And now we just plug it into our formula over here. We found the base area. We found the height. Our volume, 1/3 54 root 3 times 2 root 7. That gives an answer of 36 root 21, which is the final answer for this problem. That is our volume of our pyramid. Let's now talk about cross sections, which is one of the most powerful techniques in 3D geometry. It allows us to take a complicated 3D geometry problem and make it a 2D geometry problem. And we've already been learning how to solve 2D geometry problems. Okay, let's start off with this first example. 8 spheres of radius 100 are placed on a flat surface so that each sphere is tangent to 2 others, and their centers are the vertices of a regular octagon. 9 spheres placed on the flat surface. So as you can see here, I didn't show all of them, but here are 4 of the spheres, and there's a 9th one. And we're asked to find the radius of this last sphere. Okay, so as you see, I've got a diagram here. It's going to be really difficult to explain this complicated 3D geometry problem in this 2D diagram. If only I had a 3D model, that would just make things so much easier. Abracadabra! Where did this come from? Wow! This is a 3D model of our exact problem. That's so cool. Let's make them a little bit bigger. So as you can see, these are the 8 spheres that form an octagon, which are tangent. Assume they're touching. And then there's a 9th sphere that's touching all the other ones, tangent to all of them, and it's placed on the same flat surface. So as you can see here, they're all touching the ground. So as you can see in the 3D model, they're all touching the ground. So let's become small again so we can see the screen. The question is, what cross section do we want to take? Basically, 3D is just, there's too many things going on. Let's just look at a 2D cross section. Maybe it will give us some information. What cross section should we take? Naturally, it makes sense to take the cross section of the plane formed by the centers of these 8 small spheres. And that will look something like this. So let's imagine just slicing. Imagine I just take this and I slice through the centers of these spheres. I cut it open and I open it up. This is what I'm going to see. Okay, so the key thing to notice here is that these small spheres, these circles are all going to have radius 100. Because we took the cross section of the plane through the centers of all of these spheres. So the radius is going to be 100 of these circles. But for the big sphere, because it's much taller than the other ones, when we take the cross section, the circle that we take, the circle shown here, is going to have a radius that's much smaller than the radius of this big sphere. Let's see what that is in this top picture to really understand what that means. As you can see, these are one small sphere and one big sphere side by side. This one has radius 100. And this one has radius r. Let's just call it big R. And let's just draw these tangency radii, because they might help us later. You always draw all important radii, and these are all important radii in this diagram. Okay, So now let's take a look over here. Let's call the radius of this. Let's call the radius of this little r. This is the radius not of the sphere, but of the cross-sectional circle that comes when we slice this through. Now the question is, what is little r in terms of big R? So in this top picture, let's see what this cross-section really is. The cross-section, well, we took a plane and let's just try and draw the line. So let's use dotted line. We've got this. Imagine this line over here. Imagine taking this and then you look at it, you cut this here and you look at it open. This is a picture we're going to see. So as you can see, this little radius here is represented by this. That thing is the little radius of the circle. And this over here is 100 over here. So now the question is what is this little radius, really? So if we take a look here, we have r plus 100, and this whole thing is r. But because this is 100 here, this is also 100 here. So then if that part is 100, then the top part will be r minus 100. So that top part is r minus 100, and then from there you've got a right triangle, as you can see here. Now the question is again, what is this little radius? And let's take a look at more of the second picture right now. So what we're trying to do here is solve for the radius of the big circle. If you watched the polygons video, you remember that in an octagon, regular octagon, or really any equal angular octagon, a good strategy to extend these lines and form a bunch of 45, 45, 90 triangles, because that can give us some useful lengths to work with. As you can see, I'm extending all the sides of this octagon. So by our 45, 45, 90 ratios, this is 100 root 2, 100 root 2, 100 root 2, 100 root 2, and 100 root 2. There's all 100 root 2 by 45, 45, 90, because the hypotenuse of these 45, 45, 90 triangles is 200. Okay, so now we have this r, We're really trying to find big R in this diagram. So can we somehow relate big R to our cross section? Because over here we just have little r. We want to solve for big R. So we want to somehow include big R in our cross section here. So what length in terms of big R can we find in this cross section? We have r minus 100, r plus 100. Let's use Pythagorean theorem to find this length. Big R plus 100 squared minus big R minus 100 squared equals 200r 100 squared minus r squared minus 200r plus 100 squared, and this becomes 400r. And because it's Pythag theorem, we take the square root of this, so 20 root r, that is this distance over here. So this distance over here is 20 root r. Be very careful here. It's a very common trap. It's a very common trap to assume that these circles in the cross section are tangent. This red length is 20 root r. If you look at this 3D model, you look at this tangency point over here, that tangency point does not occur in the cross section. It occurs a little bit above. So if you take the cross section, it turns out these circles are actually not going to touch each other. So make sure you don't make that mistake. These circles don't touch each other because the tangency point is above. The tangency point is here. They're not touching over here. So in order to relate big R into our cross section, we can find this length, the distance between the centers of the two circles, which in this case is 20 root big R. And then similarly, this will also be 20 root big R. So that means 40 root big R is equal to, well, Pythag. So drop the altitude. This thingy is 200. And the height is just 200 plus 200 root 2. 40 root R is 200 squared, or let's say 40 root R squared is 200 squared plus 200 root 2 squared. And we expand, this is 1600 R. This bottom thing, well, this is just a little bit of expanding. 200 squared plus 200 squared plus 2 times 200 squared root 2 plus 2 times 200 squared. And we just clean this up a little bit. We have 4 times 200 squared plus 2 times 200 squared root 2. And now all we have to do is divide this expression by 1600 and we get our answer. So 400 times 200 squared divided by 1600. Well, 400 times 200 is 800. So that means it's just 200 divided by 2, which is 100. Now 2 times 200 squared divided by 1600. Well, 2 times 200 is 400. So 200 divided by 4, so 50 root 2. So that means R is this, and our answer is just A plus B root C, so 152. And that's our answer. Okay, so let's quickly summarize the key steps here. This was a quick. So the first step is to make a 3D model using tape and balls and stick them all into a 3D surface. So really, if you're trying to visualize this, it's often just best to try and visualize in your brain and then try to come up with some pictures and pick the right cross-section area and find information there. And the key thing here was this radius was not R, and this tangency point, the tangency point over here is not the same tangency point. It's not going to be tangent in the cross-section. So the idea was we wanted to relate big R. Somehow we wanted to put it inside our cross-sectional diagram. So then we could deal it as a 2D geo problem. And through this, we used Pythag theorem and found this length, the distance between the centers of the two circles. And then from there, it was just a standard Pythag theorem and a little bit of algebra to finish. Remember, a very common mistake, and we'll actually see this in the next video as well, is that be very careful about the tangency points. They're not always going to be in the plane, because they're always going to be perpendicular. The tangency points will be at the point that's perpendicular to both of these spheres. It's going to be above the second sphere and below the middle one. So it's not going to be in the cross-sectional plane in this case. Let's now move on to this problem over here. A right prism with height of h, which let's just say this is h, has bases that are regular hexagons with sides of length 12. 12, 12. Everything is going to be 12 across. A vertex A of the prism and its 3 adjacent vertices are the vertices of a triangular pyramid. The dihedral angle, the angle between the two planes formed by the prism, and the face of the prism is 60 degrees. We're asked to find the height squared. So what is this dihedral angle really? Let's draw some things in. Use this. Let's use a different color. So we have this pyramid over here, pyramid on the inside. And this dihedral angle is basically this angle between the two planes. So the plane that does, the face of the pyramid that does not contain A, what is that? That's this blue face over here. This face over here, as you can see, of course, it's a lot bigger, but you can imagine it's like on the inside there, that blue face. And the face of the pyramid that lies in the base of the prism, that's this purple face. Oops. This purple face over here is the face that lies in the base of the prism. So what does it mean by dihedral angle? All that means is we take the midpoint over here of this side and we connect that there. That's going to form a 60-degree angle. And let's really see what that is saying. So we've got, this is A, and this is the point below A. This thingy is the point below A. It's this point. And then we've got this face on top over here. This is the top face. This point is this point in our 3D diagram. And what all this is saying is that this angle is 60 degrees. So as you can see, what did we just do? We just took a cross section. We just took the cross section through this plane in the center. Through the A, the midpoint of this green segment, this point, and the blue point at the bottom of A. Because the dihedral angle is going to be the angle formed by the planes is the same as the angle formed by the midpoints of the sides. So this angle over here is 60, which is the same as this angle formed there in the 3D version. Of course, it doesn't look like 60 because it's a 2D drawing. This is H. Okay, so the question is, what is this length? Clearly, it goes to the midpoint of this green length. So 12, if you remember from the polygon video, whenever you have a 120-degree angle here, this whole segment will have a length of root 3 times bigger. And this is just derived from 30, 60, 90s. So this whole thing is 12 root 3. And because we're talking about dihedral angle, it's going to be we're looking at the midpoint here. Each of these parts is 6 root 3. So, therefore, we would have that this is going to be 6 root 3 away from here, 6 root 3 away from here, and this part over here is going to be 6 away, just by 30, 60, 90s. This distance is 6. So this distance, let's mark it 6 over there. And this is 90. Why is this 90? Well, because this is the top face and it's perpendicular to this because it's the right prism. So the height is perpendicular to the face. H6, 60, and then 30, 60, 90. By 30, 60, 90s, H is just 6 root 3. Our answer, 6 root 3 squared, 108. So this is kind of a cool problem where the key thing was realizing that the angle between planes, imagine you have two planes here. The angle between them is just the angle formed by the midpoints of the two planes. You imagine the midpoints of the two planes, that's the angle between those two planes. And then after that, we just took our cross section. We took this cross section here. We've got this diagram. And then it was just 30, 60, 90s. Next time, we'll talk about some more cool cross-section problems. Be sure to check out the next video. You can click on it right over there.